Okay, so good evening, students. Welcome to eighth session for problem solving on analog circuits course. So you people had concerns regarding exam, right? So for NPTEL exams, most of the time, the structure is either MCQ or numerical answer type, or you might get fill in the blanks sort of problems. These are majorly the three kind of problems that you observe in NPTEL exams. But just to be on a safer side, before starting the exam, please go through the necessary instructions that are given. Then you can start with the exam. So, can somebody confirm on which day you people have exam for analog circuits?
22nd.
22nd of March.
22nd of March, all right. So we will have one session today. There is another session tomorrow as well. Then after that, you can start your preparations. So yeah, any other doubts, or shall we begin?
Madam, I have some doubts in earlier week assignment.
Okay.
After completing your discussion, shall I ask?
Yeah, yeah, sure. We can take up the problems after the session. Okay. So if anything, like in general, if you have some doubts, you can ask now. Otherwise, if you have some personal doubts regarding any particular question or anything, we can take up the question after the session is over. Okay. So yeah, let's.
Ma'am, I had a small basic question. Can I just ask it?
Yes. What is your question?
Uh, Ma'am, it's regarding the transfer. I didn't attend much of your earlier sessions, ma'am. I could just barely keep up with the offline NPTEL videos. So
Okay.
I was just confused regarding how do you get the phase equation from the transfer function?
Phase equations, you know how to write a phase equation for algebraic equations. Like if you have an algebraic expression, how do you write phase for that? Do you know that?
No, ma'am.
How to write phase for a algebraic equation? Sorry. Um, so it's like basic. Sorry, what did I say? I said algebraic equation, right? No, no, complex numbers. If you have a complex number, do you know how to write the phase for that?
Tan inverse of imaginary part by real part.
Yes. So if you have a plus ib, this is your complex number, right? So if I have to write the phase, how do I write the phase? It is tan inverse b by a, correct?
Yes,
This
ma'am.
is how we write the phase. So in the similar fashion, see, in your transfer functions are also complex numbers, right? Just the thing is, you have real like numerator as well as denominator in a transfer function. So the only difference comes there. Now, if I say I have to write the phase for 1 plus IB, the only difference that you observe is the phase becomes minus. So minus tan inverse B by A. This is the only difference that you observe. So while writing the phase for transfer function, what do you need to know is the rules that are there for complex number phases. So how you write the phase for a complex number, where you take 180 minus theta, where you take 180 plus theta, where it is 90 minus theta, 90 plus theta, or minus theta, that thing you have to keep in mind. Otherwise, so it is same as the analysis of complex numbers, but just here you are not dealing with numbers, rather you are dealing with the parameters like r c values. But other than that, it is just complex numbers. So even the magnitude analysis that we do is the same that of complex number magnitude finding analysis. So transfer function is nothing but a complex number. You have to deal it in the same way as you deal with a complex number while finding magnitude or while finding the phase. That is the idea.
Okay, ma'am. Thank you, ma'am.
Yeah. Any other basic doubts? Okay, so if not, maybe we can quickly begin with the session, today's session. So last time there was a little concern or a little problem with the uh, this oscillator analysis. Windbridge oscillator analysis. So I'll sorry, I could not understand your concern, Ravi. Could you unmute yourself and ask? I could not get your problem. So what we are solving right now, these are previous year questions only. So the examples that we are taking or you are observing in these live problem solving sessions, these are previous year problems only. Okay. So yeah, Windbridge oscillator, right? So uh, there was a mistake while analyzing the Windbridge oscillator. So let me quickly analyze the Windbridge oscillator once again for people so that there is no doubt. So this is minus, this is plus. Okay, so this is our Windbridge oscillator. Here we take our V out from. So we already saw the transfer function, right? We wrote down the transfer function or if for so first of all, since here the input is coming from this that is non-inverting terminal, so the phase in forward path is 0 degrees. So phase required in feedback path is also 0 degrees. We only need 0 degrees phase in the feedback path also. If I talk about feedback path, for feedback path, this is V in dash, and here we have this is V out dash. So the circuit actually looks like this. This is an RC followed by a parallel RC, and here we have V out dash. This is V in dash, and if I want to find beta, what will be my beta? Or maybe I can write it like V out dash is V in dash into R parallel CS, R parallel C by R plus C plus R parallel C. So R parallel C is nothing but R into 1 upon CS by R plus 1 by CS. So here we have V out dash is V in. So this is C. Okay, so this should be 1 by CS. So R plus CS basically means R series CS. So I can write R series C. So that after writing it in Laplace transform, all of them would be in this similar structure. R plus 1 by CS by R plus 1 by CS plus R into 1 by CS upon R plus 1 by CS. So let's quickly simplify. This is dash. by CS by RCS plus 1 by CS, these two are cancelled, by R plus 1 by CS plus R upon 1 plus RCS. So here it is R1 plus RCS by 1 dash R1 plus RCS plus one plus RCS plus RCS by CS 1 plus RCS. Right, this is VR dash. So VR dash by Vn dash, this is nothing but beta, is RCS, these two cancelled, upon yeah, okay, there will be another CS also, right? CS into 1 plus RCS. Here it will be 1 plus RCS and here multiplied by CS. Yes. So here it is RCS. So it is RCS plus R square C square S square plus 1 plus RCS plus RCS. So beta comes out to be RCS upon R square C square S square plus 3RCS plus 1, right? So this is the beta. If I substitute S equal to J omega, just to separate the real and imaginary parts in my transfer function, okay? That's why I'm doing this particular thing where I'm substituting J omega in place of S. So because of that, okay. So yeah, because of that, my beta becomes JRC omega upon minus omega square R square C square plus 1 plus J 3RC omega. Now here if we observe, this is real part and this is the imaginary part. Now why we are separating them into real and imaginary part? So that is because we have to write the phase, right? What we observed, the phase required is 0 degrees. So now the phase that we need to observe from beta should also come out to be 0. Now how can I get my phase as 0 degrees? So one thing is, say if I put my real part to 0, then in beta, if my 1 minus omega square R square C square is put to 0, then what I am left with, if, okay, then in beta I am left with JRC omega by J3RC omega, right? JJ will be cancelled. RC omega is cancelled and we are left with 1 by 3. Now we know that if beta is 1 by 3, which is greater than 0, greater than or equal to 0, then what is the phase? Phase is 0 degrees, correct? If my real part is put to 0, then what is the phase that I am getting for my beta? It is 0 degrees, right? That is what I want. So because of this, what I'm doing is I'm putting my phase to, or I'm my real part to 0. So if I'm putting my real part to 0, so from here we will find the oscillating frequency. So omega square R square C square is 0. That means omega square r square c square is 1, which gives us omega is 1 upon rc. So from here, this becomes my oscillating frequency for Windbridge oscillator. This is in radians per second, and omega oscillation, frequency of oscillation will become 1 upon 2 pi rc. So this is the frequency of oscillation for Windbridge oscillator. So from here, the frequency of oscillation for Windbridge comes out to be 1 upon 2 pi rc. Is this clear to everyone? Any doubts in this? Or you can also understand it like, say, if I put my real part to 0, I'm okay. What is the doubt where you didn't understand? Can you please unmute yourself and ask? Okay, I'll explain you another way of understanding. Say you put your real part to 0. Now, if the real part is 0, then you are left with an imaginary term in numerator and an imaginary term in denominator. You know that the phase introduced by an imaginary number is plus 90 degrees if it is in numerator and minus 90 if it is in denominator. So there is a imaginary term in numerator and there is another imaginary term in denominator. Then you will have a phase of plus 90 and a phase of minus 90, which cancel, both of them will cancel each other, and you will be left with a phase of 0. Okay? So this is actually an easier way, that is equate real part to 0. So that we can get a 0 phase. I guess there was some message. Okay. So this is how we analyze it for Windbridge oscillator, and I'm sure RC phase shift oscillator all of you must have been done. There is a lot of content available already on the RC phase shift oscillator. So yeah, now since till now we have observed or we have understood harmonic oscillators, right? Both the RC phase shift oscillator and Windbridge oscillator these are harmonic oscillators. These are both harmonic oscillators. What do we mean by harmonic oscillators? They provide us sine waves, sine wave generators. So these are both sine wave generators. Sine wave means sinusoidal wave generators, right? So these are harmonic oscillators. But we discussed there were another type of, another type of oscillators other than harmonic oscillators, which are also known as non-harmonic oscillators or relaxation oscillators, right? Non-harmonic or relaxation oscillators. So these are the oscillators which give us non-sine wave generators. These are non-sine wave generators. Non-sine wave generators, by that what I mean, they are like, they can give us a square wave, a triangular wave, or a sawtooth wave. These kind of waves can be generated using relaxation oscillators or non-harmonic oscillators. Now, before starting these relaxation oscillators or non-harmonic oscillators, what we need to keep in mind is how do these circuits generate these waves, right? This is a big question. So before understanding that, let us break that whole circuit into smaller parts, okay? So I'll start from the smaller parts and then we will build on them part by part and we'll reach to these waveform generators. All right. So these are also known as waveform generators. So waveform generators are also nothing but your relaxation oscillators only. So the key component of a relaxation oscillator is a comparator. It all starts from a comparator. Now, what is a comparator? We discussed this briefly in the very beginning, in the first lecture, where we started with the op-amp, uh, and that was an open loop op-amp, where we said that there is no feedback provided to the op-amp, and we said that that particular kind of op-amp where there is no feedback, we cannot use them as amplifiers. But the op-amps without feedback, they are actually comparators. They work as comparator. So how do they work as comparators? See, this is an op-amp. Okay, you have two inputs. Now we already know that when there is a op-amp without any feedback, the gain of op-amp is very high. So if the gain of op-amp is very high, what it will do is op-amp always amplifies the difference in the input terminals, right? And but your op-amp's output is limited by plus minus VDD, right? So your output cannot go beyond VDD. So these supply voltages, or if it is one is supply and other is ground, then between these supply rails, it cannot go beyond that. Correct. So in comparator, what we do, we take advantage of that particular situation, and we say that okay, let's say I fix one of my terminals to reference. Okay, so if I fix one of my terminal to reference and say I'm providing a sine wave over here, all right. If I'm providing a sine wave over here, such that let's say my reference voltage comes out to be somewhere at this point. This is my Vref, all right, and this is the peak of the sine wave. Now see what this op-amp will do. At positive terminal, you are providing the input. You know that after a slight, very small value, since the gain of this op-amp is way too high, this is 120 dB, 180 dB, 160 dB, in that range. So definitely for very small value already, your output starts saturating. So in the beginning, if you observe, let's say since this is a sine wave, it starts from 0 at t equal to 0, okay? So at t equal to 0, your sine wave value is 0. So at t equal to 0, this is V in, right? So V in equal to 0. Now see, V in is less than Vref, correct? So if V in is less than Vref, then your output will be defined by your Vref. Since Vref is connected to the negative terminal of your op-amp, your output will become minus VDD. Okay. So if I start making a waveform of my input and output simultaneously, then how it will look like. So let's. Okay, so this is my V in, this is V out, say this is Vref, All right. This is Vref, and here we have a sine wave. Now we clearly understood that our output is defined by the level of Vref. So Vref basically defines how my output will come out to be, right? So let me divide them into time frames also for a better understanding. Okay. So first, what we observed is this is region 1. So this is this region. Right. This is first region. So in first region, when t is 0, we said that Vin is also 0, which is less than Vref. Hence, our output saturates at minus VDD, which is corresponding to the terminal that is connected with Vref. So, if it is minus VDD, say this is my level of minus VDD, right? Now, this situation will continue until Vin is less than Vref, right? Until Vn is less than Vref, the same situation will continue. So if we observe in the graph, in the first region, Vref is always higher than Vin. So that's why our VDD output saturates at minus VDD, right? Now coming to the second region, okay? So in second region, we see that Vin is greater than Vref, right? In second region, from this point till this point, Vin is greater than Vref. Now, if Vin is greater than Vref, that means my positive terminal is at higher potential than that of negative terminal. So if positive terminal is at higher potential, that means the output that we would get is positive VDD. So in this region, our output comes out to be plus VDD. So in whole of second region, my output turns to plus VDD. So this is my range of VDD. Okay. Right. Now see, if we come to third region, so in third region, Vn goes below Vref. So again, if Vn is less than Vref, again we'll get our output as minus VDD, right? Until we cross Vref, that is Vn is greater than Vref. So once Vn is greater than Vref, our output becomes plus VDD, right? Until this point. Then again, your Vn is reducing. So here again we come down with V out becoming minus VDD. Then again it goes up, right? So here, if you observe very carefully, you're getting some sort of a square wave, right? If my Vref was at 0 axis, then I would have got symmetric square wave, correct? If my Vref, rather than being more than 0, this is 0 level. If my VREF was exactly at 0, then half of input is greater than VREF, half of input is less than VREF, right? So I would have got a perfect square wave, correct? So this is the basic idea of comparators, right? Now, after comparator, what comes is a okay, so let's modify this comparator a little bit. Okay, when we modify this comparator a little bit, we call that circuit a Smith trigger. And again, that Smith trigger is nothing but a relaxation oscillator. We'll see how we convert a Smith trigger into a relaxation oscillator. But let's modify this comparator into a Smith trigger. That is the idea. So, a Smith trigger is nothing but a modified comparator. If I talk about the circuit, this is a Smith trigger. So if you observe very carefully, in this Smith trigger, there is a comparator. Like in the previous case, the same comparator is there. The only thing that we have introduced is a positive feedback using resistor values. So until now, all the circuits that we used, we saw a negative feedback circuit, right? But here, this is the first circuit wherein we are introducing positive feedback, and we'll analyze this positive feedback. Okay. So this is a Smith trigger. In this Smith trigger, if I ask you, see, this is an ideal op-amp, right? So again, since it is an ideal op-amp, the currents going in are 0. There is no current that is going inside our op-amp, but definitely we will have some current coming out of the op-amp, right? Now, if at this point I have V out, okay, and at this point, at my negative terminal, I have input. So somewhere I need to have a reference, right? So this particular positive terminal acts as my reference, which is guided by my resistor values and voltage from the output. So here the reference is drawn from the output potential. Okay. So see, what will be the value of Vref? Vref will be governed by this potential divider of Rx and Ry. Vx is nothing but V out into Ry upon Rx plus Ry. Since this is a comparator, we already know that output would be either plus VDD or minus VDD, correct? So depending on that, V reference will also have two values. One is a higher value, another is a lower value. So when V out equal to plus VDD, your Vref is VUT, that is upper threshold. Upper threshold or higher threshold, it's up to you, whatever you want to call it. So Vref is VUT. And what is the value of VUT? VUT is plus VDD into Ry upon Rx plus Ry. This is plus VUT. Now, when V out is minus VDD, then V reference will also reduce. So we call it VLT, that is lower threshold. And the value of VLT will come out to be minus VDD into Rx upon Rx plus Ry, right? This is my VLT. Okay. So all right. So now we understood that in our Smith trigger, we will have two threshold levels. That means two reference levels, and our output will change based on those two reference levels. Okay. So let me quickly draw. So say this is my V in, this is V out, this is time axis. So again, what I'm giving this Smith trigger as input is a sine wave. Okay. So there is this beautiful sine wave. Okay. And corresponding to that, we will see what are the outputs that we are getting. We already saw that there are two reference levels, VLT and VUT. So definitely VUT is greater than 0 since this is 0 level. So let's say VUT comes out here. This is VUT. And VLT will be less than 0. So VLT will come here. Alright. So now let us start analyzing this circuit. But before analyzing, we would definitely need a reference to start from, right? We would need some reference to start from. So let's consider some value of output, okay? So let's say, what do you want me to take my output as in the beginning? We need to start from some value. So let's say somehow my V out is VDD, okay, plus VDD. So if V out at 0, that is at initial state, it is plus VDD. So if V out is plus VDD, then my V ref will become VUT, right? It will become VUT, correct? So this particular reference for now is activated. Now my input is coming. So V in at 0 is 0, and it is increasing till say V peak, and then it will come down as in the sine wave. So now see, your reference has been set to VUT. That is because we said that initially the output was V out. Somehow our output was set to V out. Okay. So yeah. Now if I start analyzing for my input, which is earlier at 0, it is slowly rising until VUT. VUT is this point. VUT is this point. At this point, we will see VUT or VLT, which is compared to our inputs. So, V out was plus VDD initially, right? So, V out was plus VDD initially at 0. Then Vin is slowly rising, but it is smaller than VUT. So always our output will remain at plus VDD until the Vin crosses VUT level, which is this level, right? So as my Vin crosses VUT, so when Vin becomes greater than VUT, then when Vn is greater than VUT, this is greater than VUT, so negative terminal dominates. And our output becomes minus VDD. So this was plus VDD, right? Why is it here? Plus VDD. And so this is minus VDD. So till here it was plus VDD. The moment your Vin becomes greater than VUT, negative terminal starts to dominate and Vout becomes minus VDD. So because of this, your Vout will come down to minus VDD level. But now, see, until here, let me draw the lines for all the threshold intersecting points. So that it's easier for us to understand. Okay, this much is sufficient. So yes, we said that our output has changed to minus VDD, and that is the situation when Vin is greater than VUT. So until Vin is greater than VUT, our output is at minus VDD, right? So this is my output. Now what happens when you reach your output, or your input reaches to VUT, or the level goes down? At that point, now see, your Vout has become minus VDD. This Vout became minus VDD. which led to your V reference changing from VUT to VLT. Okay. Now V reference has also changed. It is not VUT anymore. So since VUT is not the reference, so we are not concerned about that level anymore, as that is not governing our results. So because of this, what will happen is your VDD will continue to be minus VDD until your level reaches VLT. Okay, so this is the cross section point where your VLT cuts your V in, right? Okay, now if this is the situation, after that what is happening? Your VUT, your reference level has become VLT now. Your output is at minus VDD. Now, your input is reducing. Your input goes below VLT. So, if your input is less than VLT, that means which terminal is dominant over here? If input is smaller than your VLT, that means positive terminal starts to dominate. So when positive terminal starts to dominate, so your output will now move from minus VDD to plus VDD. Why? Because your positive terminal starts to dominate. So when does this happen? When your Vin becomes smaller than VLT. Positive terminal dominates. And since the positive terminal is dominating, V out will again become plus VDD. And as the change of V out led to changing of Vref from VUT to VLT, here again your V reference will change from VLT to VUT. Okay. So now here what is happening? Your output is changing to plus VDD. Plus VDD, it will go till VLT. But now you don't have to consider VLT anymore because your new reference has shifted from VLT to VUT. So your graph will continue until VUT is attained. Then again the same cycle will repeat, and as you have reached VLT, beyond VUT, your output will go down to minus VDD. This will continue until you reach your VLT, and then it will again move up, and this will continue to be VDD, and then the same cycle repeats. Okay, so here do you understand how the thresholds are changing? And this is happening because you have taken feedback from your output. So your comparator's output is governing your threshold. That is the reason your threshold is changing. And because of that change in thresholds, you get your sine wave or your square wave in a certain way. And if you observe, the square wave is actually a perfect square wave. Right? Because if you see, like, if you consider, say, this period to that of this time period, they must be equal if your references are equally placed. So all of you, did you understand the Smith trigger?
Yes.
Do you okay. Any doubts on the Smith trigger working? Anyone? Is the Smith
No.
trigger clear? Okay. So what we did, we started with a comparator. Then we said we are modifying the comparator to make it a Smith trigger. In Smith trigger, what we observed, we found out 2 reference levels. But the next step is we need to go for a relaxation oscillator, right? And when we set,
Shall I ask one doubt?
yes, please go ahead. What is
Yeah,
your doubt?
initially we are saying output is at plus VSAT. Na? That is
Yes.
due to
It can
liquidity.
be some, see, there would be some value, right? And some error value would be there because of which your output, because it is a comparator. A small disturbance will saturate the comparator. Either it will go to plus VDD or minus VDD. So your initial conditions will always be in between plus or minus VDD. You can start the analysis from minus VDD also and then move ahead. So the graph will be slightly different. If you want me to analyze, I can analyze that for you. So here the condition was, initial condition is at plus VDD, right? Now let's say initial condition is at minus VDD. Okay. So if my initial condition is at minus VDD, that means my reference level is at VLT, right? If my initial condition, yes, so if my initial condition is at minus VDD, my reference level is at VLT. So VLT, I am crossing over here. So until that level is reached, my output remains constant. Correct? Any doubts in that?
Yes.
No doubts, right? So what I will do, we can simply draw it like this. Until here, there won't be any change in my output. Now, the moment I have reached VLT, my input is going less than VLT. And VLT is coming in the positive terminal. So that means positive terminal will dominate. So the moment my Vin goes less than VLT, my output will become VDD. And my reference will change to VUT. So here my output will go to plus VDD, and also my reference will change to VUT for the coming cycle, or coming half cycle, I should say, right? And then since this is my new reference VUT, so until I reach VUT, my output is constant. So my output goes to, it continues to be at VDD. Again, as it reaches VUT, my output will, beyond VUT, my output will become minus VDD. So it will come down. And then it will again continue. And the same curve follows. So if you observe, the only thing that changes is the initial condition, right? This slight change, this is the only difference that we observe because of the initial conditions, right? Otherwise, the whole circuit follows as it is, correct? So this is the only change that we would see. And we know, since it is a comparator, a small disturbance will also saturate the output. So we definitely know that the output will be either plus VDD or minus VDD. There is no chance other than, like, there is no situation possible other than that. So with that confidence, that's we are continuing to observe that, let's say, to consider the initial conditions also, okay, either it can be plus VDD or minus VDD. And since we always look at the steady state output, so at the steady state, the outputs remain same. So it is not a big concern for us in the initial states. Okay. Is this clear? Any doubts?
Yes.
Okay,
No.
everybody, comparator and Smith trigger clear to everyone?
Yes, ma'am.
Okay. So if you have any doubts, please unmute yourself and ask, okay? So now, till now, we have seen that we are done with the comparator and then Smith trigger. Then we said we will move to oscillator. And as we have seen that we are generating square wave. So if the square wave is generated, I can say it is a relaxation oscillator. But what is an oscillator? What was the definition that we said that we need to keep in mind? What is an oscillator?
it picks up a noise and amplifies it.
Yes. So what is it that we have to keep in mind? That oscillator does not seek any input. We don't have to give input signal to oscillator, right? But in Smith trigger, we were giving an input signal, right? This Vin is being fed to your Smith trigger, correct? So say somehow if I remove this input signal which I am providing to the circuit, if somehow I remove this input signal and something I do that it itself starts to oscillate and give me this square wave, then my this particular circuit of Smith trigger will become a oscillator, that too a relaxation oscillator or a non-harmonic oscillator, correct?
You are saying
Huh.
oscillator doesn't have any input.
Yes, oscillator does not have any input signal. You don't have to give any input signal.
We are applying the power supply, no? It is also an input.
No, that is the difference. See, power supply is a supply. Supply is
Oscillator means which generates an AC energy from DC, right, ma'am?
uh, so the idea is
By
if
utilizing DC voltage, it is generating an AC voltage.
no, that's not completely true. The idea is when we say we are feeding input, input means we are providing some signal to the circuit. So when there is an amplifier, you provide a AC signal. AC signal is not the power supply. Power supply is always needed for any device or any circuit that you design. You need power supply for working of that device. To keep the device in working state, you need power supply. But power supply is never input. Power supply is power supply. Power supply is needed to turn on your circuit. But after turning on, whatever signals you give to input, that is your input. But if you are not feeding any input or you are not providing any supply, any signal to it, then we say it is there is no input signal present. Okay. So power, so you should never say that power supply is input to the circuit. Power supply is never input to a circuit. It is just there to turn on your circuit. It turns your circuit on, but other than that, power supply is never an input. In oscillators, what it does is, we already discussed this, that in oscillators we do not provide any input to our circuit. But that doesn't mean power supply is not there. Power supply is there. Power supply is there for working of the circuit. But you are not providing any additional input to it. Any sort of sine wave, square wave, or even any sort of DC to it in the input. So oscillators don't take any input. What they do is they start with a certain noise which is always present in a circuit. It can be any kind of noise, and it picks up that noise, and that particular oscillator circuit has an resonant frequency present. So when that frequency matches the noise frequency, there are multiple frequencies in a noise. One particular frequency of noise will match with that of resonance frequency of your oscillator circuit. So that particular frequency starts to resonate and it amplifies, and at the end you get that particular frequency in your output. That is the idea. So here what I was saying is, now since we have come to say that I want a relaxation oscillator, and as we can see that Smith trigger gives me a square output, square signal, or I can say square wave output. But the only issue in a Smith trigger is I am providing an external input to my Smith trigger. But if it was an oscillator, I should not provide any input signal to my oscillator, right? So if somehow I modify this particular Smith trigger circuit such that there is no input provided to my circuit, and if I don't provide any input, then also I get a square wave output. That means I have designed my relaxation oscillator, right? So the next task is to convert the Smith trigger into a relaxation oscillator from where we can get a square wave. So let's look into that. Okay. So maybe I can simply duplicate this circuit only. So see, I don't want any input circuit. I don't want any input to be given. So somehow this circuit should get some input internally, and from there it should start to generate a sine wave. From there it can convert or sine wave or some sort of sine wave. Like it should look similar to that of sine wave, and then that will be converted into a square wave, right? So that is the idea. So how about we connect a capacitor over here? Let's say we connect a capacitor over here in input and followed by a resistor which is also connected to my output. Okay, this R. So now see what is happening in this particular circuit. Without this R and C, it was a Smith trigger. We all understood how Smith trigger is working. Everything is fine with us, right? Now, what is this RC circuit doing here? So, because of this presence of R and C, what will happen is this output, let's say your output is at plus VDD. Okay, initially, this output is at plus VDD. And we know that this capacitor is we just connected the capacitor. So there is no charge on the capacitor right now. Capacitor is not, it is simply uncharged capacitor. It has been connected via resistor. Now the moment we see a plus VDD, it sees a plus VDD potential over here, and the other side of a capacitor is connected to ground. So a charge will start to flow from the output terminal through the resistor into the capacitor. And what will happen is capacitor will start charging, right? So capacitor will start to charge. Okay. So how does this charging happen? So it is basically, the circuit is as simple as this is R, this is C. Here we have plus VDD, and simply this is charging. Now we all know the capacitor charging equation, right? Vc of t. If I ask you what is the potential across the capacitor while it's charging, the equation is Vc of infinity is equal to Vc of 0 minus Vc of infinity e to the power minus t upon Rc. If there was no resistor present, the charging would be an immediate charging, right? It is a spike charging, so it charges very fast. Immediate charging happens, and similarly, immediate discharging also happens when there is no resistor present. The moment you connect a resistor in series with that of capacitor, your charging and discharging happens with a time constant, and that time constant is defined by the value of R and C, right? So this
Madam,
is
instead of plus, you written equal to.
yeah. So this is the charging equation for my um, capacitor, right? And let's say if my capacitor is at a higher potential, so this is C and this is let's say minus VDD, okay? So if my capacitor is at higher potential and it has charged to its full potential, like plus VDD for now. So now simply it will start discharging through the resistor R. So again, it will follow the similar trend. So we will be using the same equation for charging as well as discharging, right? And how it will happen is, let's say this is my output. Maybe we can start from analyzing from the capacitor's point of view, and then we can draw the output. That would be it. So yeah. So let's say my initially my output was VDD. Okay. So my capacitor was charged to 0, and so if my output was VDD, my capacitor was at 0. The capacitor will start charging slowly, right, until it reaches a certain level. Now, what is that level? See, the moment you have VDD, here it is a Smith trigger already. So if it is a Smith trigger, we will have the reference values coming into picture. So your capacitor can charge until VUT, right? The moment your capacitor charges to VUT and the charge goes beyond VUT, your negative terminal will have higher potential and your output will flip. Correct? So your output, or I should say VC, this is VC, okay? This is VC, V capacitor, and I'll draw output by blue colored line, okay? So there is no confusion. So my capacitor charge is slowly increasing. It can reach till VUT, right? So it will increase until VUT. It cannot cross VUT. The moment it crosses VUT a little, your output will flip. So your output until this point, it would stay at plus VDD. This is V out, okay? So my VDD will now flip to minus VDD. This is minus VDD. And say here I have my VLT level. Okay. So now if my V out has come to minus VDD and my capacitor is charged till VUT, so my capacitor has higher potential than that of my output. So now the capacitor will start to discharge through the same path, that is across R, until it will go to V out. So my capacitor will start to discharge, and since my V out has turned to minus VDD, so that discharge level could go until VLT, right? Because my new reference has now changed to VLT. Correct? The moment my capacitor charge or capacitor potential reaches VLT level and it crosses the VLT level, again my positive terminal starts to dominate and my output would become plus VDD. So my output will again change to plus VDD. And it will stay at plus VDD. And if I talk about my capacitor, so capacitor again, which has discharged till VLT, it will start charging again and it will charge and go to VUT. right? And then again, it will face that VUT issue. The output will again come down to minus VDD, and my capacitor will also discharge. Right? So if we see from this particular circuit, so first of all, this has already become an oscillator. Why now this is an oscillator? Because we are not giving any internal input to it. It has become self-sufficient on its own. Because of that capacitor, it is charging and discharging and taking inputs from there. It gives us the output of a square wave. And if I talk in layman's term, so we are sort of getting a triangular wave. If we can if we can tweak my RC values a little, we can get somewhat a square wave looking wave from the capacitor charging and discharging terminal, and at the output we are getting a perfect sine wave, square wave. So we can get two waveforms from this particular circuit which are non-sinusoidal, right? So that's why this is a non-harmonic or relaxation oscillators. So is the working clear to everyone? Yes, is this working clear to everyone?
Yes, ma'am.
Anyone has any doubts? Anything that you want to ask? Anything that you didn't understand? Yes.
Here we have to use electronic capacity.
Sir, I cannot hear you. Can you speak a little louder?
Okay.
The voice is-
Okay. Here we have to use electrolytic capacitor or ordinary ceramic capacitor.
Sorry?
This type of capacitor is to be used here.
Which type of capacitor?
Electrolytic or ceramic.
I mean, anything would work. It's just that you need to consider the RC value, the time constant, and based on
Okay.
time constant values, you can switch the capacitor. So, like, yeah, depending
Okay,
on
ma'am.
that.
Thank you.
Yes.
Thank you, ma'am.
No other, there is no restriction on which type of capacitor you can use or you want to use. You can keep in mind a few capacitors from the safety perspective, but the idea is the major concern over here is capacitance values, which are important to us, because based on capacitor and resistance values only we will get the charging and discharging time constants, and based on that charging and discharging time constant we will get our waves time period. So yes, that is only of concern to us. So now did you people
Ma'am, you said something about like making the triangular looking like wave to square wave. What did you say about that, ma'am? Could you please repeat
No,
it?
no, no. I didn't say that. What I said is this triangular wave, you can tweak the time constants in a way that this triangular wave looks a little more accurate to that of an exact triangular wave, right? But more or
Okay,
less, this
ma'am.
is a little curved one, right? But you can tweak the RC value such that it looks a little more cleaner triangular wave. That is what I said. But basically, the idea is that you can get two types of waves. One is a square wave, and one is similar to triangular wave from the same circuit. That is the idea. Okay?
Madam, it is not triangular, right, madam?
No, it's not triangular. It's not
It is an
exactly.
exponentially charging and decaying signal.
Yes, it's an exponentially charging and decaying equation waveform. But if you try to tweak your RC values a little, you can make it look like very close to a triangular wave. But definitely, it is not an exact triangular wave. We will see how to make triangular waves. I'll discuss that also. So I hope this working is clear to everyone. Is the circuit clear to everyone? How the circuit is working and how we've got the waveforms? Any
Yes,
doubts?
ma'am.
Okay, if there are any doubts, please unmute yourself and ask, or else I'll continue with a slight derivation of finding out the time periods and basically what are the factors which are important to analyze the time period of this waveforms, right? Because at the end of the day, if you have a sine wave, what you want to see, your maxima and minimum values are always already defined, that is plus VDD and minus VDD. It depends on what is the supply that you are giving to your op amp. The next thing that always a AC wave or always a signal a signal which is uh, like continuously flowing through time, there are only two parameters which are very important. One is frequency of that particular signal, and another is the magnitude of the signal. Now, we understood that magnitude of this particular signal can be justified by the supplies that you provide to your op amp. It depends on that. But the second parameter is the frequency. So now, see, if you are getting a square wave, but whether you want a square wave of 5 kilohertz or 5 megahertz, 5 gigahertz, 5 terahertz, it depends on certain factors, right? So let us quickly understand and analyze what are those factors which can help us gain uh, the time period that is desired to us. Okay, for that we'll go through the derivations very quickly, and after that we'll further go into like conversion of one wave into another and all. Okay, so let's quickly go into the time period derivation. So how to find the time period? This is what we are going to analyze. So here we will start from some point. Let us consider some initial value, and from there we will see, right, how things are changing. So when V out is at plus VDD, so we are not considering the first cycle because we are starting there from zero, so that is a little incomplete. So that's why we are taking the next cycle. Okay, so in next cycle, if you observe that when V out is at VDD, our V capacitance, the capacitance potential, it uh, starts from VLT and it reaches to VUT, right? So we will substitute this equation into the capacitance charging equation to find the time constant from there. Okay. So Vc of t is nothing but Vc infinity plus Vc of 0 minus Vc of infinity into e to the power minus t upon Rc. So here Vc of Vc of 0 is the initial condition. So initial condition Vc of 0 is at VLT and Vc of infinity is at VUT, right? And we are saying that this time when your Vc or the capacitance potential changes from VLT to that of VUT, let's say I call this as T1 time period. Okay, and this condition when your capacitor potential starts from VUT and decays down to VLT, I'm calling this particular period as T2. And the total will be the time period, that is T, right? Which is T1 plus T2. So we are trying to mathematically analyze how much is T1, how much is T2. Then we will simply add both of them to find the total time period of our pulse, and from there we can say, okay, what are the factors on which the time period depends. So that is the idea that we are going forward with, right? So we see T1 is, and here t is t1, that is the period we are considering. So Vc infinity is VUT. Okay, Vc t1 is how much? So at t1s, the potential of VCT is VUT, right? So VCT1 is VUT. So here this will become VUT. Mm,
And how did you get VC of infinity as VUT?
no, VC of infinity is VUT when we are restricting it, right? Consider that there is no restriction. So maximum VC of infinity can go till VSAT, that is plus VDD, right? So if it is charging from say VLT, it can go maximum till VDD. And if it starts from say VUT and it starts decaying, the minimum it can go till is V0. So here we have to consider the extreme limits, and then we will be calculating like when t equal to t1, what is the situation. So here Vc infinity is nothing but plus VDD, or I can say plus VSAT, right? So here it would be plus VSAT. So Vc0 is VLT. So the thing is, capacitor is charging from VLT at infinite time if there is no disruption, because what has happened is here, because of flipping, the capacitor starts to discharge, right? But if we would have left it and let it charge till its full potential, it would reach till plus VDD, right? Which is plus VSAT. So yes, so Vc infinity will be the maximum value possible. So here definitely it would be plus VDD. So this is plus VDD e to the power minus T1 by RC. And here also this is plus VDD, or I can say plus VSAT, so since both are same. So VUT minus VDD upon VLT minus VDD is e to the power minus T1 by RC. So T1 is nothing but RC ln VLT minus VDD upon VUT minus VDD. I can take a minus common and I can write them as this also, VDD minus VLT and VDD plus minus VUT. This is my T1. Okay. Now VLT, we know it is nothing but minus VDD R, this was X, so RY. Okay, this is RY upon RX plus RY, and VUT is nothing but the plus VDD RY by RX plus RY. Now, say if I call this factor as I simplify this, or I call this factor as beta, then this is nothing but minus beta VDD, and VUT is nothing but plus VDD into beta. So if we substitute it over here, what we get is T1 is RC ln VDD minus VDD into beta upon VDD minus VDD into beta. So this becomes T1 becomes RC ln 1 plus beta upon 1 minus beta. Now we can further simplify this just by simply substituting the value of beta. So beta is nothing but 1 upon 1 plus Rx by Ry, or I can write Ry upon Rx plus Ry. So if I place this here, is ln 1 plus Ry upon Rx plus Ry by 1 minus Ry by Rx plus Ry. So what I get is T1 is RC ln Rx plus Ry plus Ry upon Rx plus Ry by Rx plus Ry minus Ry by Rx plus Ry. These two are cancelled. These two cancel. So T1 becomes RC ln Rx plus 2Ry by Rx. So that is nothing but T1 is RC ln 1 plus 2Ry by Rx. So the factors which are important for the charging of capacitor are R, C, Ry and Rx. Now similarly, this was, what time period was this? So this was the time when your capacitor is charging from lower limit till that of higher limit. So that is the time period T1 that we just calculated, correct? Now let us quickly calculate T2 also so that we can find the complete T. Yes. So this is the calculation for T1. Yes, this is what we did for T1. Now let's quickly calculate for T2. See, for calculating T2, we have already said that your VC of 0, the initial condition, the potential of capacitor is at VUT. And if we let it discharge at infinity, the capacitor potential will go to minus VTD, right? Or minus VSAT, anything that you want to say. Correct? So this is VC0, VCT, but the time for which the period that we are considering is actually T2. We are only going to consider the period of T2. And Vc of T2, the potential at which your calculation stops is at VLT, right? So again, writing the equation, Vc of infinity plus Vc0 minus Vc of infinity e to the power minus t upon Rc. Substituting all the values, so Vc of T2 is VLT, infinity is minus VTT, plus Vc of 0 is VUT minus VTT e to the power minus t upon Rc. Okay. So VLT plus VTT by VUT plus VTT is e to the power minus t by Rc. So if this is so T2, this was T2. This T is nothing but T2. So this T will be Rc ln VUT plus VTT by VLT plus VTT. Again, substituting the values of VUT and VLT as beta VDD and minus beta VDD, what we are left with is Rc ln beta plus 1, or I should write it like 1 plus beta 1 minus BT. This is what we are left with. This is T2, and since beta is again Ry upon Rx plus Ry, so T2 is Rc ln 1 plus Ry Rx plus Ry 1 minus Ry by Rx plus Ry. It comes out to be the similar equation, so expression also remains same. Rc ln 1 plus 2 Ry by Rx, right? So this is what we get for T2. Now since T1 and T2 we have already found, and the total time period is T. T is nothing but T1 plus T2, and since T1 and T2 both are same, so T becomes 2 times of Rc ln 1 plus 2 Ry by Rx, or it becomes 2 Rc ln 1 plus beta upon 1 minus beta. So this is the time period that we get for this particular relaxation oscillator that we just designed right now. Now, if this is my time period, then my frequency of oscillation would be nothing but 1 by time period, which is again, it is 1 upon 2 Rc ln 1 plus beta by 1 minus beta. Okay. So whatever frequency of the square wave you want, based on that based on that frequency, you can calculate the components, like fixing one component, then another component, and then finding the values of the remaining components. So that's how we design the circuits for the desired frequencies that we want. Okay, is this clear? Is the derivation clear?
Yes, ma'am. Yes.
Okay, very straightforward derivation, right? It's just we have used the capacitance charging equation, and by using that single equation, we just derived the expression, right? Okay. So after this, I mentioned that we will discuss how we can transform from one waveform to another, right? That is also something very interesting and also very important for us to analyze. So, what we found out in this particular relaxation oscillator was a square wave, right? We have got a square wave. Now, say I want a square wave, there is a square wave with me. I want a sine wave from the square wave, and I want a triangular wave from a square wave. What can I do? Any ideas, anything that comes to your mind? What can
Ma'am,
we
for a square wave to a triangular wave, we can try an integrator or maybe a differentiator.
Okay. So if we want to get a sine wave from square wave, what we can do is we can use an integrator, right? Because the moment we integrate a square wave, we would get a sine wave. But what about, sorry, triangular wave. But what about if I want a sine wave from a square wave, what can I do? Yes. Any ideas? If I want a sine wave from square wave, what can I do? Okay, somebody said if you want a triangular wave from square wave, you would use a differentiator. How would you use a differentiator? How will differentiating a square wave give you a sine wave? Sorry, triangular wave.
Ma'am, I said the other way around, ma'am.
Other way around means how?
From a square wave, if you confused between if you should use
No, no. So see.
an integrator or a differentiator. So I said both of them.
Okay.
Madam, if we integrate a square wave, we'll get triangle.
Yes.
And if we differentiate triangular wave, we'll get square wave.
Yes. But it's not like if you differentiate a square wave, you would never get a triangular wave. So it's like how it is. So once you have, let's say you have
It
some more.
depends on time constant, madam.
Yes. Um, Not really, but it's more like
We have
how.
three conditions now, madam. RC less than tau, RC greater than T,
Huh?
RC.
But still,
Based on that, it will generate three different signals.
no. But how would differentiating a square wave give you a triangular wave?
No, no, no. If we integrate square wave, we'll get the triangle, madam.
Yes. Yes.
Reverse one, if we differentiate triangular wave, it
Yes.
generates a square wave.
Yes. But it is not true that by using a square wave, if you differentiate it, you will get a triangular wave.
Like when I differentiate T, I'll get one, na, madam, with some amplitude. D by
Yes.
dt of T is nothing but one.
Yes. Yes. So that is the thing.
Positive
So
going
if you
ramp will generate positive step, negative going ramp will generate negative step.
so if you have these kind of impulses, so these are practical impulses, okay? So practical impulses would have very small width and peaks. When you have these kind of practical impulses, if you integrate them, you would get a square wave. And again, if you integrate them, we would get a triangular wave, right? So this is again So here again, if we integrate, we'll get this triangular wave. So this is square and this is triangle. So what can be done to obtain a sine wave from a square wave? Or do you know how to obtain square waves from sine wave? Oh well, anyways we are done, right?
Yeah.
But what? Sorry?
How you do Schmidt figure, we can get square root for any periodic wave.
Yes. By using Schmidt figure, you can get a square wave by using a sine wave. But do you know any other way to which you can get a square wave from sine wave? Do you people know any other way in which you can obtain a square wave from sine waves? Schmidt trigger is one, I agree. What else can be done?
Madam, comparator. You can compare.
Comparator and Schmidt trigger are more or less the same. Any other thing that comes to your mind, any other way? Other than comparators, Schmidt triggers, any other possible method that comes to your mind? Okay. So if I ask you, how do you write a square wave in Fourier form? What do you say? If I ask you to write a square wave in Fourier form, how would it look like? Yes, Fourier series of a square wave. So if does anybody remember writing a square wave as maybe you can directly write. Does anyone remember this kind of representation of sine wave? Where we had some sine, some cosine, odd even harmonics. So actually the idea is square wave is nothing but a combination of sine waves. Combination of sine waves, okay? Sine or cosine waves, it's because there is no difference in sine and cosine wave. So we always call them sine waves, okay? combination of sine waves. So now if I tell you that square waves are combination of sine waves, so can you give me a way in which I can get a sine wave from square wave? If I have a square wave, I can extract sine wave out of it. If I already tell you that square waves are nothing but the combination of sine waves, what can be done? Yes. Anything that comes to your mind?
Differentiating.
How differentiating would help?
You're taking a small part out of it, so you maybe get a sine wave.
So you call it a differentiator? Or will it be something else?
Madam, adder or integrator?
Sorry?
Adder or integrator?
Integrator, but square wave, the moment you apply an integrator, you will get a triangular wave, right? You will never get a sine wave.
Then adder, you add the sine wave, you get square wave.
We discussed this already. Maybe last week's lecture. Can you relate to it? Last week's lecture. What we discussed last week? We discussed filters, right? Can you think of anything with respect to filters? Yes.
Bandpass filter?
Yes. We can have a bandpass filter with very high Q and low bandwidth, such that it only passes a single frequency. If it only passes a single frequency, then that bandpass filter can be used to extract a single sine wave out of multiple sine waves present in a square wave. Okay, so we can do bandpass filtering with high Q. High Q basically means high selectivity. Q is nothing but selectivity. Very high selectivity. We discussed notch filter, remember? The band stop filter, where it only rejects a single frequency, we called that particular filter as notch filter. So similar to that, like as the notch filter rejects one particular frequency, if there was a band pass filter which passes only a single frequency, that particular band pass filter, if it is designed, then that band pass filter can extract one sine wave out of the square waves, the multiple square waves present in the signal. Okay, so what will happen if you integrate this triangular wave further? If let's say you integrate this triangular wave further, what will be happening? So this is, the slope is t, right? Now the moment we integrate it once again, the slope becomes quadratic in nature. So the behavior will more or less look like a sine wave. It is definitely not a sine wave, but it might appear like that. But it will be quadratic in nature. It is not sine, but it will be quadratic in nature. Okay. So this is how basically you can design a complete set of waveform generators. By using one generator, you can extract multiple waveforms from that. Now, if it is a triangular wave, and if I tell you I want a sawtooth wave, what will you do? So we have done triangular wave, we have done sine wave. I want a sawtooth wave. What is sawtooth wave? It is somewhat like this. Okay. Something like this. something like this. So it is not symmetric, basically. That is the idea. So how would we get a sawtooth wave? What will we do? Yes, what can be done to get a sawtooth wave? We can also get this sawtooth kind of wave from here also. This from this relaxation oscillator also we can get that sawtooth kind of behavior. The only thing is we don't want symmetry. That means if one path is used for charging, we should use some other path for discharging. So what will happen is your charging path and discharging path are different, because of which your rise time and fall time will be different. So you will see somewhat a sawtooth kind of behavior. And if you observe the output of that particular circuit, it will not be a square wave anymore, the symmetric square wave anymore. Rather, the on time and off time of your sine wave would be different. So it affects your duty cycle of the signal. Now, when we say duty cycle, it is also something very important. And duty cycles can be put to use in many ways. So when we say duty cycle, it is on time upon t total. Okay, so on time on t total. If t on equal to t off, and we know that t total is nothing but t on plus t off, right? So if my t total is t on plus t off, and if t on equal to t off, so my duty cycle d would be how much?
50%.
Yes, 1 by 2. So 50%. So t total would be 1 by 2, that is 50%, right? This is case 1. Now in case 2, if I say my t on is twice of t off, then my duty cycle becomes 2/3, right? Which is 66.66%. And if it is other way around, half of t off, or t off is twice of t on, then my duty cycle becomes 1 upon 3, that is 33.33%. So this is how your duty cycle changes. Now, based on this changing duty cycle, this can be put to use in many ways. Like where you want your on time and off time in similar fashion, there you can use 50% duty cycle. If you want your signal to be on, stay on for a longer period of time, you can use higher duty cycle, more than 50%. If you want your T on to be less than 50%, like you want your pulses or your signal to be on for very small times and the off times of the signal to be very large, you can use lesser duty cycles. This can be used in graphics designing, your series lights, and even your fans, like fan speed regulation, and all these can be done through duty cycle implementation by changing the duty cycles. So duty cycle is
Excuse
also,
me, excuse me,
sorry,
madam. Excuse me, madam, these wave checking ICs are inside the function generator in the lab.
sorry,
All these ICs are there inside the function generator in the laboratory.
which IC?
These different circuits are used to generate different waveforms.
Right, right.
So that ICs are inside this function generator device.
Yes, definitely. Inside the function generator, you will have oscillators, and what exact circuit is there inside oscillators? It is sometimes given in the like the data sheet of the function generator itself, but more or less they will be using similar kind of circuits, but might be more complex for better efficiency and everything. The advanced function generators that we use in lab, they must be using these kind of circuits, but the circuits might be a bit more complex for better optimization and estimation. But yeah,
Okay,
definitely
thank you,
more or
ma'am.
less similar kind of circuits.
Okay, thank you, ma'am.
Yes, more or less similar kind of circuits. And there might be ASIC chips inside, so which are application specific chips, which are not generic in nature. Like generic chips are NAND chips, NOR chips, timer ICs, or these ICs are generic that you can find in anywhere. But the systems that you use, or say the your laptops and any other circuits like say function generators or anything, they would be using specific chips. We call them ASIC chips. They are application specific
Application
chips.
specific.
Yes. So for the particular application, they must be optimized in a certain way with the parameters. So they are more of ASIC chips which are there, but more or less inside the ASIC chips, the basic functionality is similar to that of what you analyze. Yes, the circuits will be more complex with much more optimization and accuracy for getting better optimization and accuracy. But the basic physics remains more or less the same.
Okay, thank you, ma'am.
Okay, so it's already 7 o'clock. Um, we discussed a lot of things today, but we could not go to problems. So tomorrow, since we have another session, so I'll take up the problems based on this multivibrators also. And when we get these kind of square waves, we call them astable multivibrators also, where you get a square wave. Or
Madam, about my doubts.
okay, yes, we can take up the doubts now because don't want to go into the problems. We'll do it tomorrow. So yeah, what were the doubts?
I have
No, I
just
have
one
doubt
small question. Can
regarding
I?
week 7 assignment, ma'am.
Sorry, week
Yesterday
7.
I asked me.
Okay,
Due to network connection, I disconnected.
yes, okay. So I guess I finished that doubt already. So yes, what was the doubt, anyways? So we discussed. I analyzed that problem. So what I found out is when you have same values for the resistors, what is happening
Hmm.
is you don't get anything in the numerator. You only get in the denominator. So getting the required phase condition is not possible in that particular case. But when you have different values for resistors, what is happening is you get some factor in numerator and some factor in denominator. So when you have both numerator and denominator, and say you are calculating for phase, you want a certain value of phase. So you will get positive as well as negative phase, right? So there is a possibility that both of them might cancel each other. But if one is there is no term in the numerator, you only have a denominator term, then you only get a single signed phase, right? So because of that, there is a thing that you can never achieve. Like there is this condition that there is a possibility, but that is impossible. So when the resistor values are same, the condition becomes impossible. But when the resistor values are different, there is still a slight possibility that for some combinations, it might get true. The condition might be satisfied. So there is still a possibility of doubt over there. But when the resistor values are equal, it is cancelled out completely. So that there is no possibility at all. It is impossible. So that is why in one case it will oscillate, in other case it will not. That is what I could analyze, and I finished that day with that particular statement only. So maybe you can look into it because that analysis is already there. So yeah, you can go through. Any other doubts?
Yeah, yes, madam.
Yes.
Uh, In week 3, question number 5, madam.
Maybe you can bring up the questions.
Yeah, okay.
The question.
Shall I share my screen, ma'am?
Yes, yes, please do.
Problem is visible, madam.
Yes.
This question number 5, they're asked what type of feedback given to op amp in the circuit and find the feedback factor beta.
Yes. Okay. So what is the doubt in this? What type of feedback is this?
Hmm.
Yes, what type of feedback is this by looking at the circuit?
Output is connected back to the negative terminal. Am I correct, ma'am?
Yes,
So negative feedback is present, right?
correct.
And feedback factor is R1 divided by R1 plus RF. Am I correct?
Yes.
But they are given positive feedback as the answer. Look at this.
How come it is a positive feedback?
I don't know, ma'am. That's why I'm asking. They are given that.
No, no, no. How can this be a positive? See, you understand feedback, right? When
Yes.
output is fed to input, and whichever terminal you connect your output to, that type of feedback it is. Now, since here it is connected to negative feedback, how can it be a positive feedback?
Is there any ambiguity in that small signal model which they kept in the problem, madam, in the figure?
No, that cannot be the case.
They are written op amp output as V1 and V naught as minus
Okay,
V1.
so because they have given it as minus V1.
Excuse me, madam. Excuse me, madam.
Yes.
What I feel it is basically a split trigger with positive feedback. There might be some mistakes in it is inverting split trigger. There might be
Sir,
mistakes in.
I could not hear you. There is a lot of noise.
Okay, okay.
Maybe you can type. Is
I
it
feel that
possible
it is a inverting split trigger. There may be mistake here in the sign or P2 and index.
So one thing might be fine. The other thing that I can see possibly is that what they are connecting to in the small signal model to V out they are connecting minus V1. So that basically means that V1 was fed to this. Say this is a transistor model, okay? So to the transistor's input, I can share my screen. So to the transistor's input, what is happening is, but
Madam, will you?
maybe you can get it clarified once in the like. So you people didn't raise any doubt like what is this? Maybe you can ask them for a clarity. But yeah, as you mentioned, one thing that I can understand is this was plus, this was minus, right? Here it is connected. Here this is V1, and then when they are using the small signal model plus minus, they have given minus V1 over here. This minus
That small signal model of whom, madam, actually? Is it for op amp?
no, 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 no. This is some transistor or something has been connected over here. So this small signal model corresponds to that. So the feedback is given. So first, op-amp's output is supplied to a transistor or some device it is. Okay. Some three-terminal device. So most probably it should be a transistor. Then that particular transistor's output is given as your output, and that output is being fed back to the op-amp. So one thing I can see is, since here they have mentioned that the output V out is getting is minus V1. So here it was V1, but V out is minus V1. And then when you are feeding it to negative, so at this point, when it goes inside, it becomes minus V1. Then again a minus because of the negative. You're getting my point. So that is the only way we can say it is a positive feedback is, see, if it is A, again, this is your input side, and from here you are feeding it. Okay, and here, say this is some beta. Here you had V out, right? Then, but rather than giving it to beta, what they did is they passed it to through something, some gain based circuit, and you are getting minus V out over here, right? And this minus V out is being fed to your beta circuit, and that is again being fed through this negative to A. So at this point, what is being fed to your amplifier is minus of minus V out, which becomes plus V out, right? Now, in place of this, say I had this kind of mixer where it was V in, and this is positive feedback. For positive feedback, I'm representing it with a plus, right? And this is A, and then here it was a beta, okay? And this is minus V, minus of minus beta. Here also this will be a plus B beta, right? So here if it goes V out, then when it is fed by beta V out is fed to beta, it will become beta V out. Here this was minus beta V out. And then when it is passing through this positive feedback, what is actually going into your amplifier is plus beta V out, right? This is happening when you have positive feedback, correct? But here what has happened is, here the feedback is negative, but what is actually being fed to the input is equivalent of that of a positive feedback.
Shall we call it as an amplifier, madam? If we provide positive feedback.
It is still an amplifier, it's just that it will become unstable for sure.
No, madam. If we provide positive feedback, gain is not under our control, so output will be saturated, right? It never amplifies.
Yes, that is what I'm saying. It will become unstable.
Uh,
That is the situation. But based on the condition that they have given, that this minus V out that is happening, no. Because of this actually, even though you are giving a negative feedback, the equivalent result comes out to be as that of a positive feedback.
no. What can we give the name of that circuit, madam?
I mean, see, at the end, whether it is a positive feedback or negative feedback, looking at the circuit is one thing, but at the end, what we want is the behavior out of it, right? See, in this case, although it appears to be a negative feedback, because we are connecting the output directly to negative terminal of the input. But if we talk about the effective impact is that of a positive feedback. Because when you analyze the circuit, you will analyze that the behavior it gives is similar to that of a positive feedback.
Excuse me, madam. Excuse me.
Yes.
What I feel, madam, is actually since output negative, it is
Sorry?
inversely, since output is negative. Output
Yes.
is negative. So it is inverting slip switch. Basically comparing the two things. One by potential divider and another some unknown AC signal at the inverter.
Your voice is not clear.
No, I don't want to name it that casually, because looking at the circuit also, it's not that straightforward as I can see, because there is a transistor kind of device over there, which is basically more or less it's an inverter there. So it's like
We are very much
followed by an
confused.
inverter.
Madam, we are very much confused about this.
So that is what I'm saying. So the thing is here, if I talk from a circuit's point of view, what is that circuit? The circuit is basically an amplifier followed by an inverter, and then that inverter's output is being fed to your amplifier again. So what is happening is, we know that amplifier generally gives us a phase shift. So it's like a CS amplifier, say. CS amplifier gives us a phase shift of 180 degrees. Followed by, if you keep an inverter, it will nullify that phase difference. But the moment you are feeding it to, you are using a feedback, but you are
Madam,
the feedback that
madam,
Park House will not satisfy. Yes.
madam, there we are seeing only small signal model. We don't know whether that transistor is an amplifier or switch, or we don't know now.
Yeah, but you know the output, right? You know the impact, because it is given that in input you are getting V1, and in output it is extracting minus V1. And that minus V1 is actually translating to your V out, which is again being fed, right? So that 180-degree phase shift involvement can already be observed there. So from
My
there,
doubt is, madam, we can see only phase shift, but magnitude is we can see the amplified version.
mm, I mean, definitely after that, if the magnitude, because the signal has increased, because of which it would saturate, as it is going to the positive feedback. Because it's, see, when we say positive feedback means you are adding something to the input which is already present. Negative feedback means you are actually deducting something from the input which is being fed. That is the idea. So since it is a positive feedback, definitely the output will saturate. But from
If
the,
output saturates, how can we say it's an amplified version, madam?
no, so you're not asked about the analysis, right? You are only asked about the feedback thing.
From the analysis only, we can conclude that whether it is amplifier or oscillator or negative feedback or positive feedback. Am I correct, ma'am?
No, that is not always true, right? I analyzed here. No, how did I say that? The moment I saw the connection of output to that of op amp, I said it was a negative feedback, because I didn't consider anything in that op amp's output and that small signals part. I neglected that. Once I neglected that, I said that this is a negative feedback. But the moment we are considering that component which is present between the op amp's output and that of the terminal from where you are giving feedback, there is a bit tricky, right? And you need to analyze based on that. So this particular analysis, as you can see from here, do you understand how we are getting the behavior of positive feedback? In both the cases, case A is where what your this is showing, right? So this is V out dash. So this is what is given in the question, and B is for positive.
That small signal model is there in the feedback path, ma'am.
Yes. So we can consider that the small signal model is there in the feedback path, and from there we can analyze. More or less, it will be the same.
No, eighth question, madam.
Eighth question. No,
is
your
this-
screen is not shared. You need to
Ah.
share it. So it's more or less, so it's not like just by looking at the circuit, straightforward, it appears to be a negative feedback, but because of this negative, it is actually the impact, effective feedback, if I talk about, then it comes out to be positive. But maybe if you still have doubt, you can raise a query in the forum, and let's see what the course TAs have to say about it.
I kept in the forum, but they are saying that you can ask in the problem solving session.
Oh, okay.
That's why I'm asking now.
So from my
See,
understanding,
madam, is my screen is visible?
no, I cannot see your screen.
Okay, once again I'll present my screen.
Okay, but is my explanation satisfactory to you? Do you understand how the equivalent positive feedback behavior is coming, which is similar in both the cases?
Yes, ma'am, that is okay. But how can we know that is in the feedback path or in the gain path? And it is small signal model of transistor or which element?
More or less, it should be a transistor because it's a two-port device.
By seeing that minus sign, we cannot conclude. No?
No,
From
phase
that, we can understand that 180 degrees phase shift is there.
Yes.
But we have to see the magnitude criteria, right, ma'am, along phase shift.
For what?
If the condition A beta should be less than 1, then only it acts as an amplifier, right, madam?
Oh, okay. So you're saying, what if that Barkhausen criteria is satisfied and it moves to an oscillating phase? That is
Yeah.
what.
Yeah.
Okay.
Now these are the questions I posted in the forum, madam,
Okay.
and they replied me like, see, they kept the problem solving session. They kept this message.
Oh, okay. Okay, anyways. So from my understanding, like what I understand and how I can explain is through this. But can we think of some other method? Then I have to look into. But
Madam,
question 8, I don't know which question it is.
I'm showing, ma'am. I'm showing in the screen.
No, I cannot see the question.
Okay, I'll share my complete screen, madam.
Yes, you share the complete screen. That is that.
I think
If
now it is
people have
visible.
a lot of doubt, then maybe we can skip tomorrow's session. Tomorrow, anyways, there is another TA who will be taking the session, so we can take up the doubt problems.
Yeah,
They
this one you
also-
can, ma'am.
Okay, this circuit. Yeah, what do I have to do?
They're asking Z1, Z2, madam.
Okay. Right. So here you have to use Miller's concept.
Yes, madam.
Yes. So what is the doubt there?
Now, how to find, madam? I got different solution. What they are given in the solution, madam.
So what are they giving in the solution and what is it that you are finding?
So as per Miller's theorem, this capacitor feedback capacitor at the input side, it will be C into 1 minus K, where K is the V naught by V in, right, madam?
Gain A.
Oh, this capacitor, feedback capacitor at the input side, we can write it as C into 1 minus K, right?
1 minus A. 1 minus gain.
K means it's a ratio of V naught by V in.
No, it will be gain of the op-amp.
No, you explain, ma'am. I will listen better.
No, I'm saying capacitance will come into, like when you distribute a Miller capacitor, so one part will come in input, another part will come in output. So the
Yes,
part
ma'am.
that comes in input is C into 1 minus A. A is the gain of the whatever amplifier is there.
Okay.
And on the other side, it will be 1 minus or 1 plus. I'm getting a bit confused. 1 minus, 1 plus, 1 upon A in the output side.
Output side, what, ma'am?
1 minus or 1 plus minus may you can check it once, and 1 by A is the factor that comes in the output side.
No, madam. Actually in the explanation, they are given C into 1 minus 1 by A.
Huh. Okay.
But whereas in the solution, they are given it as directly 101. I will open the solution also, then it is clear to you, madam.
Okay, maybe you can open.
See here, madam.
Huh.
They are written it as at input side C into 1 minus A, where V naught by V in they are given it as minus 100. So that's why we got plus. If you
Yes.
see on the bottom, madam,
Huh.
if it is 1 minus 1 by A,
Okay.
then it will be 99 by 100, right, madam?
So lekin
My doubt is, will you explain me about C2, madam? How they are written 100 by 101?
So how did you get this? So if it was C1 is minus A, and you had no doubt when they wrote 1 plus 100, then when you are saying C2 as 1 minus 1 upon A, why do you have doubt when they are writing it as 100?
Yeah, 1 minus 1 by 100, right, madam?
So
Then
what is
100 minus 1 divided by 100. It is 99 by 100. They wrote 100 by 101.
No,
I
but the
don't know.
gain is minus 100, right?
Yes, madam. If it is minus 100 also, 1 plus 1 by 100, right?
Yeah, 101 by 100.
Then 101 by 100, right?
Yeah.
Then they wrote 100 by 101.
Okay, so what is the answer?
I got different answer, madam.
No, but what is there in option? May do you have your answer?
Yeah, options I'll show you.
There were some corrections also, right, in few of the solutions.
They are not corrected this, madam. That's why I'm asking. So they are given option as this one. 980 divided by s plus 19.6. They are given second one. I gave last one, madam. Z2.
Okay.
The screen is visible, madam.
Yeah. Mueller's theorem. C into 1 minus 1 पर नहीं ही होता है. Amplifier gain was negative, positive.
Positive, madam. Minus 100. Sorry, negative minus 100, madam. They are given it as minus 100. They are given in the problem V0 by VA as equal to minus 100. C is 10 microfarads and R is 50 ohms.
Okay. So if it is minus 100. What they have written is 100 upon 101, right?
Yes, madam. But it is actually 101 by 100, right, madam?
Yeah, 101 by 100, or either it would be 99 by 100, depending on the plus and minus.
Yes, ma'am. But they wrote 100 by 101.
Yeah, 100 by 101 is something. Oh, but there was this other capacitor also in series, no? The whole RC you have to solve, right?
Yes, madam. That they are written. See here.
So here Z2 is the combination of all of them.
Yes, madam. They are writing only C1, C2. That capacity is already there here, C2. They are not disturbing the earlier capacitor values, madam. Using Miller theorem, the feedback resistor, they are represented as input side C1 and output side C2.
Okay, yeah. But okay, yeah, I get your point. Like in denominator, how can you get a bigger number? When it is, yeah, I get your point. Yes, that is true. Yes, maybe you can raise this again. Did anybody solve this other question? Like, did anyone get the correct answer? How did you solve? Anybody? Somebody was saying they have solved, right? What? Okay, Z1 is C1 minus A. Then we need to do 3 parallel. Yeah. So no. That the question is he will do the parallel things later. The concern that is, Ravi, are you still there?
Here I am listening.
Okay. No, the other Ravi. So Ravi, what his concern is in the solution, we already know that through Miller capacitance, when it comes in output, it should have 1 minus 1 by A as the factor, right, into C. So when it is 1 minus 1 by A into C, and if we are saying that since the gain is negative, it will become 1 plus 1 by A, right? So that is 100 plus 1 by 100. So it is 101 by 100 times C, right? How can the value will become 100 upon 101? That is his concern. So, how did you solve that?
He left the meeting, madam.
Oh, he left that meeting.
Now he joined.
So yeah, how did you get 101 by 100? Did you get 101 by 100 as given in the solution? Because I sort of agree with you that how can numerator be, no, denominator was larger, right? 101 was in denominator. Okay. 101 is in denominator, correct? Yeah. 101 should not come in denominator as far as the formula is concerned. That's true. Okay. That should not come like that. We did parallel finally. Structured some example values.
This is correct, madam.
Okay, so sorry.
It is 101 by 100 only, right, madam?
Yes, because in denominator you are only getting a factor of a, right? How can it be a factor of 101? How will you get 101 in denominator? There is no way possible. In denominator you will get 100 only. Unless there is no. Yeah, in denominator you will get a as a factor. So it is 100 only in it will come in denominator. It should not be a 101. What he is saying is they did some substitution and eliminated the options. Rather than finding the correct options, they simply eliminated the options and then solved it. That's how they got it.
If it is C by 1 minus 1 by K, then their answer is correct, madam. But it is, according to Miller, it is not correct, right?
What is it that you are saying?
If it is C by
C
1
by,
minus 1 by K, then we'll get their answer, madam. But as per Miller theorem, we have to write C into 1 minus 1 by K. So many mistakes are there, madam, in solutions. That's why I'm asking these questions. If I'm troubling, I'm sorry.
a minus 1. Okay, so there are actually different ways of representation also in Miller's theorem. But a upon 1 minus a, so this is. Hmm. In lectures, what was the formula given for Miller's capacitance?
They are given C into 1 minus 1 by M, ma'am. There they are taking Y admittance, and
Oh,
at the admittance they are written at the input side Y into 1 minus K.
but
They are
if it's
taking
admittance, then if you make it resistance, things will change, no?
in the tutorial, I mean in lecture, they are taking Y, madam, parameter, and with the help of Y they wrote the equations.
So if it is,
Y into 1 minus K, and output side Y into 1 minus 1 by K they are written.
so if it is admittance, then resistance would be opposite to that, no? 1 by would be the resistance, no? Impedance. Because there is a relation between admittance and impedance also, right? Y is 1 by Z. it is admittance. No, in output it is C into 1 upon 1 minus 1 by A only, I guess. Because if A is very, very large, in output side C out you get it as C. But if that is the factor here also, then also you will get this 1 minus A output side. No, because if admittance is inverse of impedance, right? And if you are finding the impedance, then you need to go for 1 by that. Yeah, it is an admittance factor, no?
They are written this, madam. Simply they wrote y.
But this Y is admittance, right?
Hmm.
But we are looking for impedance factor. Then impedance is 1 by admittance.
Madam,
So we
we
would
are
need.
talking about capacitor now, madam. We don't have a resistor or something else for
Yeah,
calling
yeah.
impedance or admittance.
No. But see, 1 upon C is impedance. XC that we write, no? XC, or for C when we do the Laplace, when we do the transform, the 1 by Cs that we write, it is corresponding to the impedance. It is not corresponding to admittance.
As per your point of view, if you take like that, even for input side also it should be different, right?
Then it is 1 minus K. If it is 1 minus
At
K,
input side, we are multiplying C with 1 minus K, and Y it will change at the output side. At the input also it has to change. If you are talking about in terms of impedance.
second. If it is Y 1 minus 1 by K Y times K minus 1 by K for this. That is, it would be K upon K minus 1. Okay, it is 1 minus K. So how can it be admittance?
Then your voice is not audible. Not audible. No.
Audible, madam.
Hello, madam. Hello, madam. And what we did is we convert that Miller's into C into 1 minus 1 by A. Then we did parallel of 3, and we get one equation. And then we randomly substitute one value on that equation. Then we check that same value with the options. Then we came across option B. Then we tick that.
No, madam, no one asked. Because the questions given in the assignment are not relevant to lecture notes, madam. Strictly speaking.
Madam, in assignment, in oscillators, they didn't even tell that concept, madam. All questions.
Yesterday I asked
Assignment.
them giving some circuit whether it oscillates or not oscillates.
Madam, could you please explain that once? Because we did a lot of time and we get answer, but they said doesn't oscillate. Could you please explain one question, madam? Hard go. No, madam. No. Madam, we can understand within 1 minute, madam. Please explain within 1 minute. Madam, okay, madam. Let me give me answer.
The
Is this
problem is that
assignment
in exam,
answer?
if we got this type of questions, it's difficult to solve, na ma'am. That's why they are asking. Still, I have doubts in week 4, week 5, week 6, ma'am. We'll discuss tomorrow. Because you are saying it is late. Ma'am. Okay. Thank you.
Okay, thank you, madam.